So let's get started. So homework one due next class on Thursday, right? Thursday morning. And then I have added problem 4 about SO3 and SU2, which is a very important problem for physicists. So I highly recommend you at least try to solve it. Do you know SO3 or SON? Maybe I can explain today a little bit. How many of you guys have taken the quantum mechanics? Oh, most of them. And then have you learned angular momenta quantization? I don't know, depending on people who define the angular momentum commutation relation Li, Lj is equal to, did you learn in quantum mechanics? Oh, okay. Then you learned something about the SO3 rotation. You must have learned. Okay. Okay, last time we give a definition of manifold. So we give you a definition of manifold and also submanifold. And I just give you the example of the sphere. So today I will talk about the map and also vector field, tangent space and vector field and so on. Okay, so let's get started. So let's define the smooth map. So given a two manifold, M is m-dimensional manifold, and N is n-dimensional manifold. And usually, so as you can, we want to generate like some map between Rm to Rn, which you guys are familiar with. Well, smooth function. So we want to construct a similar thing for manifold. But that's easy thing. Locally we already know some M and N, and locally it look like patch inside Rn. So we can make use of this open patch to construct the smooth map. That's what we are going to do. So that's what we are going to do. So let's consider the two manifold. Let's go M. Let's go N, whatever manifold is. Not necessarily two dimension, but just schematically I just wrote down the shape of manifold like this way. And take the chart in, let's pick P, point P here. And just look at the open neighborhood. Maybe I should write down like this way, like it's open. And then consider open neighborhood around the point P. Okay. Then, so we know that there is a chart. So this is one chart of the manifold. And we know that there is a map, phi, which map to some inside Rn, some open patch. So this is I call it some U alpha by alpha. And then smooth map is just a map from M to N. It's a map. So there must be the image of point P. So it's mapped to somewhere else. So around here. This is F of P. Okay? And we know this is a manifold. So there must be some chart that contain f of p. Okay, let's call this one is the b beta. Okay, b beta. I think to distinguish u and b, I always put the bar on u. So this is pi alpha, u alpha. And then there's a map, I call it psi beta, that is inside of Rm. Now there's an open patch, open subset inside of Rn, which is, so this is phi beta p. And then there's an open patch. And this is the image is also, of course, psi beta, b beta. So therefore, this point is map p goes to f of p goes to psi beta, f of p. Okay, you understand? So then so one can we know that this is one-to-one map, right? Invertible. So therefore, so any point inside of the open patch can be moved to one-to-one there's a one-to-one corresponding point. So you can have an inverse map, and by using map f, and go to this point. Okay. So then one can construct a map between Rm to Rn open patch, just composing phi alpha inverse f and psi beta. Okay. Phi alpha inverse f psi beta. Okay. That is a map from this open patch to this open patch. So note that everything are different word. Okay. Everything sits in different word, but this map make a bridge between them. Okay. This map. And since this is a map from open subset Rm to the open subset Rn, one can differentiate. Okay? And if this map is smooth for every point p, then f is called smooth map. So this f is smooth, or some people call C infinity map, or some people call differentiable. Map. So, but smooth is easiest way to create it. I just use smooth map. If any point p, for any point p, this the composition phi alpha dot f dot psi beta is smooth. Smooth. I mean this map, I think I should write down phi alpha inverse f dot psi beta is a map from if this is smooth. If for any point p, this map is smooth. So even if you can take some other point, whatever, let's go q, one can take another open patch. Okay, open patch. And then, of course, f is a map from m to n, so there's an image, okay, to the n. And then f of q. And then consider there must be one chart that covers this point f of q. And then again, you just bring it to the Rn, and then look at the composition map. And if it is everything smooth, we call f is a smooth map between m and n. So we just make use of all the chart to define the map. And in particular, if f has smooth inverse map F inverse such that, of course, the composition F dot F inverse, F inverse is n goes to m. And of course, n goes to n, and F inverse is n goes to m. Then F is called diffeomorphism. So in this case, dimension has to be the same. So m, small m, in this case, m has to be equal to n. In this case, this is the condition. Okay, so let's look at the example. So what is the example of diffeomorphism? Let's consider diffeomorphism of, diffeomorphism. So can you give me some example for manifold and the diffeomorphism? So the one example is you consider so S2, and you just consider S2. There's a axis like this way, x, y, z, y. Usual physicists will call it, and then you can just consider rotation around the x-axis and the y-axis, rotation around the y-axis and z-axis. So this is, of course, a generator is Lx, Ly, and Lz. So this is what you learn in quantum mechanics. Generator of this rotation is called Lx and Ly and Lz. And then, did you learn this one in quantum mechanics? Do you? Just tell me if you don't. You miss a chance. If you learn it, it's okay. So if you consider rotation around the x-axis and y-axis and z-axis, everything, this forms the diffeomorphism group. So given that F and G are both diffeomorphism, okay, then composition F dot G or G dot F, they are not necessarily equal, are both, or also diffeomorphism. Do you understand? Do you understand? So for instance, rotation around the x-axis is diffeomorphism of S2. And they form a group so-called SO3. That's called SO3. And of course, if you generalize the higher dimension, and then now I cannot write down the axis properly. If you consider n sphere, one can also consider, so this can be defined by U0 square plus dot 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 plus U1 UN square is equal to 1. Therefore, one can also consider the rotation on the U0 axis, U1 axis, U2 axis, and so on. That form the group of SON. That's called SON. We will learn Lie group and Lie algebra later, but you should know at least the terminology of special orthogonal group. So this is special orthogonal group. And in particular, so in the case of the SO3, it's very important for quantum mechanics. So as you know, let's see. So if there is a symmetry, there is a quantum quantity, and then if the system is rotationally symmetric, angular momentum is conserved. Okay. So that's e to the exponential whatever, depends on notation 2 pi I generator Li. So this is a generator of rotation around the I-axis. Okay. So that's what you learn in quantum mechanics, presumably. Did you learn it? Some people just nodding. Yes. Just say yes if you learn. If you don't learn, you just say no. It's okay. Don't be shy. So that's one example of diffeomorphism. Can you construct a diffeomorphism torus? Last time, I introduced torus by identify the edges. How do you, can you construct diffeomorphism torus? Can you construct diffeomorphism of torus? So usually torus, this is T is called T2. So I want to construct a map, smooth map, which is invariable between itself. T2 cross T2. Can you construct the diffeomorphism? Just mapped from one torus to the other torus or itself, except identity. Huh? Good. So what he said is, so it's just a torus is just the rectangle with the edges identified. So it's you can consider some consider a rectangle on R2. So therefore, you can just translate the point like this way. Every point for one direction. Of course, so this point goes to this point. This point goes to this point. That will give a map from T2 to T2. But of course, it's invariable because you just go back to original point, and it's a one-to-one map, and it's smooth. Okay. Okay. So that is actually this is actually I'm going to explain. This is called flow of the vector field. This map is called flow of vector field. So for instance, so one can consider the direct product of the two manifold, and you can consider projection. Okay, so you just consider product of a manifold. M and N are the manifold, like we assume, and then we can just project to the one of the component. That's called projection map. That is also smooth map, but not diffeomorphism unless either M or N are point. Okay, do you understand? Okay, and something very, very interesting one is for instance, given the M and N, so you can just, this is a schematic. So given a smooth map, M goes to N, and you just consider the product. So this is the schematic diagram for M cross N. Then, so one can consider the map. So we have the smooth map. So let's assume this is smooth map. And then one can construct a so-called submanifold inside M cross N in such a way that the each point on M there is a map to N. So there is a map to some F of, so this is a point inside of M, and it's mapped to the N. So this is the slice. That is the one copy of M. and there is a point f of p, which is the image of the point p under this map. And each point one can, so each point one can, for instance, q, we take q, there is a point f of q inside of this one copy of n. Then at the end of the day, so you just, if you look at the read of all the point, the image of all the point under this map, one can construct a graph for which called gamma of f. So do you understand my construction? So each point in M, there is an image into the N. But we now consider the product of M cross N, okay? Therefore, so the M can be just mapped inside M cross N as a graph, as a submanifold. So this is a called graph construction. It's called graph of smooth map F and cross N. But this is very important. Well, like a yeah. So important map one can consider when you study topology. Any questions so far? Okay, so let's move on. So manifold with boundary. So as you can easily imagine, so this is Riemann surface with boundary. The boundary is here, and if you take this point, you can have open patch, as I mentioned last time, to construct manifold. But now you have a boundary. Okay. If you have a boundary, you can pick a point on the boundary. Now, point on boundary. Now, if you look at the open neighborhood, you only have half disk, right? So this can map to upper half plane by continuous map, continuous invertible map. Okay. So to construct the manifold with boundary, so that the boundary point is mapped to the upper half plane. Usually people write down like this way. If this is n-dimensional, like this way, which is time component, x, let's call this direction is, my notation is what? xn. So this is xn. So xn is always greater than or equal to 0, and this boundary point is mapped to when x mapped to this line or plane. X is the boundary point is mapped to the plane, but the point on the plane which is defined by xn is equal to 0, which means this plane, okay, n minus 1 plane. Okay, you understand? So for instance, yeah. So that's how you define, and I'm not going to explain everything about the definition of the manifold with boundary. So it's intuitively obvious. Okay, intuitively obvious. So given the point on the boundary, it's only mapped to the xn is equal to 0 locus, and look at the neighborhood. And of course, if there is an overlap region, again, go back, point in here, go back to here, and map to here, and so on. And that is smooth map. and so on. So I'm not going to write down everything, but intuitively clear, hopefully. Okay. And so the important thing is that the one can consider the submanifold, which consists boundary. Okay. If you consider the boundary, all the map is mapped to the boundary here, which is Rn minus 1. Okay? And then again consider open patch. So if you pick a point here, everything you can consider local chart, which is open in Rn minus 1. So therefore, the boundary of M is n minus 1 dimensional manifold. Okay. Do you understand? Any question? Do you understand? So since the all boundary point is always mapped to Rn minus 1, open locus of the chart in the one chart in the boundary is always mapped to open subset in Rn minus 1. And one can construct a smooth map, therefore it's manifold. So it's a submanifold, n minus 1 submanifold inside of M. For the simple construction is that if you consider Dn is the x inside of Rn, let's go. So this is an n plus 1 dimensional disk, and then what is the boundary of disk? Speak out. And sphere. Okay? So it's a manifold. Okay, any questions so far?
So the open patch in the patch in the boundary, is it open set or closed set, or?
Good question. So it should be open. It should be open. So his question is that the one I have written down. So so your question is, since this it includes this line, whether it's open or closed. Let's see. I really forgot the. My knowledge of topology, basic topological space is already becomes weak. As far as I remember, it should be open. I need to check, but I think it should be open. Yeah, it should be open neighborhood. Yeah, but I'll check later. Any other questions? Okay, so now let's move on to tangent space. Tangent space. Okay, so given a point P, so M is the manifold, as we assume, and pick a point P. So one can consider Okay, so then, okay, tangent vector. First, let's consider tangent vector. So pick a point P, so the tangent vector xp is called tangent vector satisfy the following. So xp is actually the map from some smooth function to R. So the notation C infinity of M is all the map from M goes to R. Smooth. So this is the notation I'm going to use. C infinity of M is this set of all smooth map. And then the tangent vector xp is a map from smooth map to R. I'm going to explain what it means. And if it satisfies following condition linearity, so which means that given the two functions, so f and g are smooth function, and let's consider a and b are some real number. Okay, it's a real number. Then, of course, a times f plus b times g is also smooth function. Do you understand? Do you understand what you mean? Do you understand? So f is a map from M goes to R. G is map from M goes to R. Okay? And then AF, so therefore AF plus BG is apply is the also M goes to R, which defined as AF plus BG at the point P is just a AFP plus BGP. Do you understand? Do you understand? Okay. Since R, in R, you can have multiplication and also addition. It's indeed field. So you can just multiply A into the value of R, and also you have addition. And this here I use multiplication of R, and here I use the addition of R. Do you understand? So therefore, this is element of the smooth map from M to R. Okay. So then one can apply x of AF plus BG, and the linearity means A xp of F plus B xp of G. Okay. Do you understand? And then, so the important rule is Leibniz rule. So again, given that F and G smooth map, F times G is also C infinity. So F times G of P is of course FP and GP. So here I use multiplication of R. Maybe wrong. Let me think. Is it composition or not? It should be multiplication. Yeah, it should be. What I have written is correct. It should be correct. So therefore, Leibniz rule is xp it satisfies this is called Leibniz rule. Okay, understand? So this is two conditions it should satisfy. Looks like, I mean, when I first try to read the mathematics book, it always starts definition and then lemma proposition. At the end of the day, it becomes theorem and so on. It looks like boring, but it has a meaning. So I will explain what it means actually. So what it means is the follows. So this, have you ever heard of Leibniz rule in the literature previously? No? Okay. So Leibniz rule is a typical property of the first derivative. So for instance, let's consider m is some okay, m is r, and then so for instance, so let's assume m is r. R is also manifold, as you can easily, the simplest manifold, and f is r cross r, some function, which means some function. And G is function R cross R. Let's see. So let's take some examples. So what kind of function do you want to consider? Just give me some function. R to R. Okay, let's consider x squared. So which means that the x goes to x squared. So give me another function g. Huh? Okay, sine x, sine function. This means x goes to sine x. Okay, what kind of operator? Let's look at the what kind of operator xp we need to take. Okay, we need to take. For instance, I can give you answer immediately. For instance, ddx. Let's look at the different satisfy. Apply ddx. Apply on f and evaluate at the point p. That's the candidate for xp. So f is equal to. Let's define like this way. So then let's look at the example. So f and g are, we pick x squared and sine, right? So let's look at if this one satisfies property 1. Let's check the property 1. So let's check a x squared plus b sine x, and you just apply ddx and the point p. So this is left hand side of linearity. And as you can easily see, so this is first derivative, so it doesn't see the a, right? So you can just immediately apply a acts on ddx x squared, okay? And it satisfies linearity. So it can act on this one immediately without looking at the v, just v plus b ddx sine x, okay, and evaluate at point p. Okay, as you can see, it satisfies linearity. Do you understand? And then let's look at number 2, Leibniz rule, whether it's satisfied. ddx acts on x squared sine x. Okay, evaluate at point p. Okay, point p means x just substitute some value on x. Okay. How do you do the first derivative? you just apply ddx on x curve first. 2x sine x at point P, x is equal to P, plus ddx acts on sine x, right? X curve cosine x is satisfied that means rule. Do you understand? So let's look at the other example. If you define, what if you define like this way? Does it satisfy the definition? What's wrong with this definition? Leibniz rule is not satisfied. So one is okay. You can always linearity differential operator. This just second derivative satisfy the linearity, but it breaks Leibniz rule because if you do the ddx curve, ddx can act on this one and this one. Okay, so there's a term something like plus 2x cosine x at point P. So this one does not appear in right hand side. Okay, therefore this is the definition excludes second derivative. You understand? Or higher derivative. So if you look at the definition, it looks like boring, but each definition has its own meaning, and you should understand what it means. Only they should not. I mean, try not to memorize everything, but try to. If you understand the meaning, so automatically you will understand what it means. The meaning of what the tangent vector means. Okay. So let's move. So furthermore, so the tangent vector form the vector space. So given the xp and the yp, both are tangent space, tangent vector. Usually people both tangent vector, then axp plus byp is also tangent vector. How do you know that? Go ahead. Go ahead. How do you know this one is tangent vector?
It also satisfies linearity of the Magnus Strip.
Yeah, so this one, you just need to check this one satisfies 1 and 2. I mean, you can do the same exercise. I mean, xp plus byp just acts on alpha f plus beta g, and then this is equal to, I mean, xp alpha f plus beta g. I mean, it's boring thing, but one has to check. And then apply so both are tangent vector. So we just show this one is alpha x b. Sorry, no, why I have written b p. I mean, it's boring to do, but you should check. So this is the condition. So therefore, what I'm trying to do. So this one is this is the linearity, and you can do the same exercise for Leibniz rule. I'm not gonna do that. Therefore, this is also tangent vector. And also, this is also tangent vector. So therefore, this means that if you call this is all tangent vectors at point P in manifold, this form vector space, form a vector space. So it's form of vectors. Okay. This is form. And it's called, and this one is called tangent space. It's called tangent space. Any question? Okay. If you have question, if you don't understand something, or if you understand something, just speak up. So, and the people often write as follows. So this is a manifold M, and pick a point P. Pick a point P. Tangent space is actually the tangent space. It's really come from. So you just embed the some manifold M in high dimensional R. That can be done by some theorem by, I already forgot what, Whitney's theorem, and just look at the tangent space of this embedding. So that's an intuitive way to understand the tangent space. But to make it more precise, so one can just consider consider the curve inside a manifold. For instance, you have some segment. Whatever segment is inside R, you just pick some segment, A to B. Remember, A to B, 0 to 1 is also okay. 0 to 1 is, and whatever segment, let's call this one is I. And let's map gamma. I goes to, oh sorry, then minus 1 to 1. Let's pick minus 1 to 1. Whatever it is, it's okay. Oh, this is a segment inside R. And let's call consider smooth map from I to M. Okay? And where gamma of 0 is equal to P. Which means that this segment this is mapped to the manifold M like this way. So minus 1 point is mapped around here, and 0 is mapped to point P, and 1 is mapped around here. So that's a segment it's mapped. So it's called curve inside M. Okay. So this is a smooth curve. Curve in M. Smooth curve in M. I didn't include in my lecture note. I didn't include minus 1 and 1, but I just put the open one, whichever. I mean, it's not important. And then one can take and then one can define as the tangent vector acts on F as follows. So the tangent vector defined by this curve is as follows: ddt gamma of t you understand what it means? XP defined by this curve. Do you understand what it means? So, as I mentioned, F is a map from M to R. Therefore, this M is mapped to some R. Unfortunately, I don't have a place to write down R, so I will erase this notation. And then, so this is the R. And the whole map is, manifold is mapped to R under F. Okay? So then, so one can compose, so -1 to 1 is mapped to by gamma. Okay? This smooth curve. Okay? These points are mapped to R. Okay? Something like this, and sometimes it can be like it's a very, very complicated function. It can be. So this composition, gamma F, the T is an element. T is an element in this segment, -1 to 1. Okay. T is mapped to gamma and F by composition of the map. So it's a map from segment to R. Okay. So one can differentiate. So segment to R, so it's some open set in R to open set in R. Okay, so one can differentiate. So differentiation, it makes sense. And the thing I missed is this is t equal to 0. Did I write correctly? Oh, okay, good. So this, that you can do. Okay. So this is the, and it turns out that this satisfies, and one can check. Linearity and Leibniz rule. Okay. So that's actually automatic, almost automatic, because it's the first derivative. It's first derivative. We already knew. Check in this example. The first derivative satisfies linearity and Leibniz rule. So we almost already checked. So this is how. So xp is a tangent vector defined by the curve at the point P. Okay. This is one can define the equivalence class. For instance, there is another curve. Let's go gamma 1. Another curve can be something like this way. Okay, so another map. Let's go this gamma 2. So if gamma 1 of 0 is P and gamma 2 0 is P, and the derivative so this means that at this point, a tangent vector, literally tangent vector is something like so here, tangent vector is something like this one, okay? If they're a tangent, they satisfy this condition. Phi is a local part. So phi is, oh my goodness, I cannot write. Phi is open chart around here and map to phi is open subset in Rn. Yeah, this is map. It just phi is the open. So if two curves satisfy this condition, they define the same tangent vector. Okay? So if they have a defined, so therefore tangent space can be defined as follows. This actually if you consider if gamma 1 and gamma 2 satisfy this condition, maybe we can just call it their equivalent at the point P. Then this actually indeed satisfies, this relation satisfies the equivalence relation, so-called. Then the tangent space, I'm very glad that this course becomes like a 3 hours, or like how does it? 2.5 hours or 3 credits or whatever. The last time it's only 2 credits, so I need to be a bit hurried. So now I can explain slowly. So tangent space can be all curve, all smooth curves. Gamma such that gamma of 0 is P and mounted by equivalence relation. So this means that so if you can consider all smooth curve that actually goes through the point P, but if they satisfy this condition, if they satisfy this condition, you identify the curve. Okay, that's what you mean. So if they have the same tangent vector, you just identify. That's what you mean. That's another way to define the tangent space. So this is schematic way of writing a tangent space. This is TPM. And the blue one is the XP. This XP, the set of all the tangent vectors form the vector space, so it can be understood the tangent space at point P. And every point one can define every point on M one can define tangent space. And unfortunately, somehow this is not working. It's not working. Okay. So given the local coordinate, so from here, given the local coordinate, yes.
Why in the definition of the two curves are tangent? Why this? So if at point P, if the two tangent vectors are opposite, the two curves are also tangent. So why there is not an absolute value of this derivative?
I mean,
so even they are opposite.
For instance, one can define the following map. For instance, one can define -1 to the 1. There's a map. Is there -1? Just sign map, right? You can just flip -1 to the -1 and just flip opposite point. And then compose to this one. Then that define the vector space is something like opposite. -xp. So they are different. So if you use absolute value, it's as a vector space, they are different objects. Okay. And given a local coordinate, physicists likes local coordinate. So the last time I introduced local coordinate, oh yes, then xp always can be written as a sum of xpi physicists always write like this way, where the xpi I'm going to write. So xpi is ddt xi gamma of t. Do you understand? So partial x1 p dot the partial xn p is a basis of this vector space. So TPM a vector space. So one can define a basis. So this basis is defined by the choice of local coordinate. Okay. So given the basis, so in the vector space B, you can pick the basis E1 dot En. Then any element in vector space B can be written linear combination of the basis. Okay, that's what you learn in the linear algebra. This A1 to AN corresponds to this part. Okay, and this part is first derivative of the gamma with respect to local coordinate xi. Do you understand? So let me write down the so for instance gamma is, so this is n, and it's point pick a point P, and you have open local chart is mapped to about phi, okay? Phi, and which is inside Rn, you have a x1, xn, xn, and so on, okay? And P is mapped to, for instance, the origin, so there's a phi is mapped to this open subset inside Rn, okay? Then what we have done is that the consider curve, so there's some segment here is mapped to the curve around here. Okay? Is mapped to curve like this way. Okay? This is a composition of gamma and phi. Gamma and phi. And the phi is the collection of the local coordinate. x1, x2, xn. Okay? Each one is mapped to R, inside R, okay? So therefore, segment is mapped to manifold first. We don't know how to define the derivative, but once you use the open chart here, one can define the derivative, okay? That will give you your coefficient. Do you understand? That's how you define locally, write down the locally the tangent vector. Oops. So for instance, so this is not the today this week's homework, but I'm going to next homework, do this one. So for instance, in homework, SU2 is defined by A is 2 by 2 matrix over C coefficient such that the A and the A dagger is equal to 1. And then in homework. So A can be written as, for instance, alpha, beta, beta. And then one can check and such that the okay, that's SU2, for instance, SO3. And this define indeed some kind of rotation. So this matrix alpha beta minus beta star alpha star acts on the vector E1, E2, just multiplication, and EI are a complex number. So it's defined indeed it define the rotation in complex world. SO3 is the A is 3 by 3 matrix such that the A transpose is equal to 1. I think this is enough. So sorry, 3 by 3 and real coefficient. Therefore A can be written by 3 by 3 matrix. I'm not gonna write down everything, but which satisfy this condition. So whatever, A11, A22, A33, and so on. Sorry, A12, A13, sorry. I'm not gonna write down.
So this is also determinant equal to 1.
Which one?
SO3.
But this automatically give you determinant equal to 1. Huh? Oh, yeah. Yeah, thank you very much. Thank you very much. You're right. Yeah, you're right. So this SO3 is a rotation, as I mentioned. So for instance, X rotation, as you know, the rotation around the X axis is defined by cosine theta, sine theta, minus sine theta, cosine theta, 1, 0, 0, 0, 0. This is one of the elements. And so on. So that's a composition of the X and Y and Z. Okay? This itself, so look at, so these are the element in R, right? So definitely this is inside of manifold R to the 3 by 3 9. Okay? There's definitely some cross sum, indeed it's a cross sum manifold inside SO3. And you need to understand the dimension. You need to understand the dimension of this manifold and so on. And in quantum mechanics, you can just always write down. So Li, Lx is equal. And I'm going to put the h bar to be 1 so that the p is something like a so this will give you some differential operator, okay? So essentially, Li is epsilon I j k xj partial xk, right? I think I hope I'm correct. Up to some sign, up to some I, maybe I or something. That's yeah. So this really looks like the one I have written here. It's a tangent vector I have written down. Okay. And in the next homework, you will see that the indeed the tangent vector for SO3 is the it's really related to, so this tangent vector or this manifold is related to angular momentum in the next homework. So seems like what you're doing is completely different from physics at this moment. You may have an impression that what you are doing is totally different from physics, but already if you look at the simple manifold, this is SO3 is a group but manifold. It's called Lie group. And look at tangent space. And you will see in the next homework, it's related to the theory of angular momentum. That's what you're going to see. So what you're learning now is very, very relevant to physics. I mean, I'm not giving a definition or totally mathematics to make you bored. I'm not going to do that. I'm just trying to connect everything what I'm talking to physics at the end of the day. So just be patient. Any questions so far? Okay. So, and if you learn general relativity, you already familiar with you already familiar with the log coordinate transformation. For instance, let's use this figure. So so let's see, one open chart, and one can take another open chart, something like this one, is mapped to psi, and as far as I remember, blue is not visible so much, so let's use yellow. So it's mapped to yn, y1 in some way. So then there are two ways to define the express this tangent vector xp. So one is the xp is equal to, in some coordinate xpi, pressure. And the physics should be independent of the choice of coordinate. So some people can be written, some people choose some other coordinate, but they should be independent. And you should know about the coordinate transformation between them. NP. Okay, so then how they are related to is as follows. Let's see. So x tilde j partial yj, or p is xj tilde partial x partial y. Sorry, I'm already getting rusty. At point P, and this, the summation over j will give you this is equal to xip without tilde. So this is usual coordinate transformation you learn in general relativity. Do you understand what it means? So if you compose psi inverse and phi, x can be written in terms of the function of y. Okay? So this is a map from y to x. Okay? Now for y, x can be written function y, so you can make sense of derivative with respect to y. Okay. Then if you sum over j, I'm using Einstein convention now here. I'm too lazy now. So I'm using Einstein convention. So j summation over j is the same. Like I'm with summation, and this summation will give you xi without theta. Without theta, this one. Okay. That's a Fourier transformation. So the physics should be independent of the choice of coordinate. Any questions so far? And this one is called, sometimes called Jacobian. When did we start? Shall we take a break? Let's take a break. So please be careful here. Please be careful, camera. Yeah.
I understand why Magnus Strip is gamma curve. Yeah, Magnus Strip is defined by gamma. I think it's
I'm sorry? All single curve, which satisfy.
Why is it
No. All smooth curve divided by this equivalence class. It's divided by equivalence. This equivalence class is satisfied as well.
Equivalence means that the two curves share the same
Tangent. Yeah. But there are infinitely many tangent curves. I mean, if you have a point here, there's lots of curves that share the tangent. So you have to identify everything. Equivalence class by equivalence.
Another question is that gamma is a curve. And if there is pieces, the gamma will be a segment. It should by its pieces segment.
Yeah. Yeah, I mean, locally it's curved, right? I mean, the point here, and if you look around here, it's locally just top. Local. What do you mean segment? What do you mean segment? Yeah. It's of course there's the end and the final point. The starting point and the final point. But including starting point and final point, I call it just curve. Yeah.
这就是这个上水的这个，然后呢，为了 I equals from minus y is necessary. I mean, it can be any open segment.
Whatever.
Yeah.
Whatever. Even R is okay. R is okay.
And the definition is just for convenience.
Yeah, just.
因为它是 this tangent plane the set of vector.
Tangent space set of tangent vectors. That's also another way to do it. Set of curve divided by
So in I mean this. So we define the equivalent curves, and so that's the true curves and satisfy our relation. So in the traditional infinite space, so that they are in the same plane with the vector.
So they share the same tangent vector.
So the vector they are the same vector, or the vector they are all in the same plane.
What do you mean?
I mean the equivalence. So the vector in the traditional space.
Euclidean space.
Euclidean space, and so the vectors are the same or the one plane. This. We have two curves, and we have tangent vector. So we have the equivalence. Equivalence means the two vector they are in the
No, it's the same. Define the same tangent vector. The dual space I will introduce later. Don't worry, it's called tangent vector. Okay, let's resume. So now I introduce tangent space. What I'm going to do is the you consider tangent space at the ones. I mean, you just you consider all the tangent space together over the manifold. So is the union of P set up. Schematically you have so M. At each point you have a tangent space TPM. At each point you can consider tangent space, and you just consider all together. And schematically, if you consider Tm, and at each point you can consider tangent space. So you just, it's not tangent, but just rotate whatever 90 degree or whatever. I mean, rotate a little bit, and at each point you just look at now it's no longer tangent, it's just orthogonal. But to consider as a family of the tangent space, I just write it like draw it like this way. And at each point you have a tangent space. And you can just, so you just consider, and then, and it looks like a really bundle. It's called bundle. And you can put so-called topology in there. And then this one is called a tangent bundle. So this is a tangent bundle of M. And tangent, so this tangent bundle itself can be understood as a manifold, non-compact manifold. So Tm itself, tangent bundle, is a manifold of dimension 2n. Of course, m dimension of m is the same as n. So that can be intuitively clear, right? So on one direction, there is an n direction, and on the tangent vector space has another n dimension. N plus n is 2n. So that's I mean, I have written down how the coordinate transformation and so on, and should I explain it to you? Then let's do that. It's a kind of bit boring, but so for instance, one can take So given pick a point P, let's see. So pick a point P. P in M, you have TPM. And then since this is manifold, you can take one open chart you call U. And now we just consider the just projection map pi. So you just forget about everything. All the point of the tangent space goes to the original point. I mean, the point on M. Okay? So that's a projection map. Okay? Then if you consider the inverse of U on the pi, so it becomes, so all the bundle, which is something like all the bundle contained in this region. So this is pi inverse of U. You understand? So everything corrupts under pi. Everything corrupts to the M. But if you look at the inverse of U, so I promise you, I put the bar to distinguish U and V. So pi inverse U is another open subset inside a Tm. Okay, you can put some topology and it's open subset. So then, one can just write down. So what I did is U is something like U here, and there is a map. Phi of U inside Rn. Okay. Rn. So this is the what you open chart, one open chart around the point P. But you can extend U by using this the projection map by pi. Okay. Then one can just define the map from pi inverse U to U in such a way that the so phi of U times Rn. Okay. Do you understand what I mean? So each point, okay, each point is somewhere around here. It's mapped to some phi of U, point in phi of U. Okay, but now we have a phi of direction. It's called phi or tangent space direction. So this direction on R is parameterized by this space. Okay. So this is a map. Did I call something? So I think there's a typo here, but anyway. For instance, xp can be written something like x. So under this map, so what I'm trying to do is try to map pi inverse of U into open subset inside R to N. Okay? So then R to N, then if you satisfy this property of manifold, like a transition function smooth, one can show this tangent bundle itself is a manifold. Okay? And this map, pi inverse inside an open subset in R to N is one copy is just phi of U itself. Another copy is tangent space direction. You have to parameter the tangent space. So phi of U only know about how the open neighborhood around P look like around this manifold itself. But we don't know what's going to happen if you use only this the phi. So we need to know about the information of this tangent vector direction. That is encoded in this one. And this map is mapped to x1 of p, xn of p, and xp1 dot xpn. Okay. So the first n component is just a map to the point in phi of u, but the other component is just define a point in Rs. Okay. Then this map will give you the open subset inside R to n. And one can check. So we already know that it satisfies under the coordinate transformation. You just have a smooth map. Okay. Then you have a nice smooth transition function, and then you can just obtain you can see that this T of M also satisfies the definition of the manifold, which I'm going to omit. It's the lecture note I have written down explicitly, but I'm going to omit. So transition function is also smooth. I call this map is phi tilde in the lecture note after typo. Any question? So now, I need it I could have made a right decision to make it this 3 credit instead of 2 credits. Now I think if it is 2 credits, I have to bit rush. So now we can define vector field. I briefly explained the vector field at the first lecture. So the vector field can be understood as the smooth correction of this tangent vector. So what I meant is that given the manifold, at each point there is a tangent vector, xp. Okay? And you can smoothly as you move the point in M, you can smoothly change the rough idea is smoothly change tangent vector smoothly, okay, and so on. Smoothly. At each point, you have a tangent vector, and at the end of the day, anyway, it's just schematic. At the end of the day, it defines the vector field all over the manifold. Okay, that's called vector field. And the right way to define is there's an M and a tangent. Let's see. Tangent bundle T of M. Okay. At each point, you have a fiber or tangent space. So at each point P, you have this vertical line is just the schematic diagram of a tangent space, TPM. Now, so you have a projection map, Tm goes to N. The projection map, you just shrink the whole tangent space to the N. You just shrink to the N. Okay, that's a projection map. But there is some kind of opposite way of doing it. It's similar to graph I have written down before. So one can define the section, so-called section. Section, I call it X, and yeah, let's call X, section. So that the map from M to Tm. So M is some manifold here. At each point, one can define some map P goes to some point around here. And at each point here, one can define the point So this point is mapped. Point in M is mapped to point in Tm on the fiber direction. On the fiber direction. At the end of the day, so one can define the so-called section. So this x of M satisfies the following thing. So the condition we impose P is mapped on the fiber, the point on the fiber. So therefore, the composition x dot pi should be equal to what? Identity. Good. So composition x is just mapped to the point on the fiber. The pi is just shrinks to the original point. It should be identity. Okay. So the section should satisfy this property. Then it define this. So it's a vector field. So at each point, you pick some vector. So each point is pick xp. At each point, let's go q. You have xq. Okay. You can define xq. Okay. So that's what we have done. So each point, you have defined each point p. You define xp. Each point q, you define xq. But now this x is smooth map. So as we already know, M and Tm are both smooth manifold. Okay, so one can define a smooth map, which satisfies this property. So it's smooth map. So therefore, as you move around the point on the base, it's the M is called base. Anyway, base of the tangent bundle. As you move around the point in M, so the vector field itself, tangent vector itself moves smoothly. That's what it means. So it's smoothly. It doesn't become like this way. Okay, that's what it means. Okay. So now something interesting happened at this point. So what's happening at this point? Just stop. What's happening at these 2 points? What's going to happen tangent vector? Tangent becomes what? 0. So at this point, the tangent becomes 0. Vector becomes 0. At this point, I don't know where it is, but let's assume this point and this point. At this point, tangent becomes 0. So the first lecture I have written down the vector field, whose 0 point is north pole, south pole. Like this way, right? At the first lecture. At the first lecture, north pole and south pole are 0 of the vector field. Therefore, they correspond to these points. Okay. Example. So Sn is the n sphere. Let's consider n as n sphere and the vector field, which is defined by, let's see, x0. So we just consider the vector field. I don't know why I call it. Okay, let's call x. So now this is the way I just express the local coordinate. So one can define, so xi is something like minus x1, x0. When n is even, n is odd, and if this is the even, I just define the same thing at 0. Yeah. So this is n is even. So this will define the smooth vector field. So let's look at the S2 case in that case. S2. Do you understand what I'm doing here? So S2 case is exactly when k is equal to 0. Okay? K equal to 0 means that the vector field xi, so S2 case, particular S2 case, vector field is minus x1, x0, and 0. Do you know what I'm doing here? Can you draw the vector field on the 2 sphere? So here, x2, x1, and x0. How the vector field look like? Where's the 0 point? Can you draw?
It rotate around the C.
Yeah, x-axis, good, wonderful. So it's rotation around the x2 axis, wonderful. How do you see? Do you know how to see that?
The Z component is
Z component 0, but is that all? So for instance, this point is so this point is
orthogonal to
yeah x1, x0, and x1, and the vector field is orthogonal to this vector. So if you take the inner product with that one, you get 0. So it should be orthogonal. So everything orthogonal to this equator. The same thing. So it's independent of x2. So therefore, if you just write down a circle, it only depends on coordinate x0 and x1 direction. So if you take so it becomes the orthogonal to this circle. At the end of the day, you have the vector field that generates a rotation around the x2. Okay. See, it's getting closer to quantum mechanics. That's what you learn in quantum mechanics. So till what time should I go? Like 4? 10 plus 10. Okay. 10 past 4. Okay. Okay, I have 15 minutes. So long. Good. So usually people mathematics literature is the set of all vector field, set of the all section. So this is called section. So this called section of the bundle. So people just write down this frac x of m is so people sometimes gamma of Tm, the set of all sections. Section satisfies this condition. So, usual literature, we're going to generalize the notion of bundle into lighter, a so-called vector bundle. And one can also consider section of vector bundle. Always section, usual notation of section is this gamma. But in particularly for the tangent space, sometimes mathematicians often use frac x. Anyway, that's just notation. And then, since this is a collection of the tangent space, the vector field x. So this is vector field. It's a vector field on M. Okay. So this is vector field. So a section is a vector field, or vector field, all the vector fields, whichever you call it. All the vector fields, all section, whichever you call it. Is a map. So X is a map from C infinity of M to C infinity of M. I think I'm correct here. Which satisfies the following condition: X alpha F plus beta G. So the reason why, so the last time when we learned in the first half of lecture, the tangent vector is a map from function to R, right? But now we collect all the point on over N, okay? At each point, the tangent vector is a map from C infinity of M to R, okay? But if you collect everything, at each point the map is R, and if you associate R on each point and smoothly move to around the over the manifold, everything becomes the infinity map of M. So we associate P goes to R, but as you move around the P smoothly, so at the end of the day, map is, so we define a smooth map, M goes to R, okay? That is an element inside of C infinity of M, okay? Therefore, if you move around the P around the smooth manifold, at the end of the day, we define C infinity of M to C infinity of M, okay? And that satisfies the following condition. So this is linearity and Leibniz rule. It's just an extension of the so. Do you understand what I mean? Okay, I think I should explain in the following. Some people do not understand what it means about C infinity to C infinity look like. Okay, so then the function defined, okay, so this is, let's consider, so this is the element of C infinity of M, by definition. And you just consider graph. I mentioned graph, right? Graph is what? You just consider the product of M cross R, okay? And F is mapped to some like this way, right? Like this way. F is mapped to, this is gamma of F. It's a graph. Gamma F, okay? So what I did is that the R is, so So what I did is that the xp of f is an element in R, right? So given the point P, so you associate this point is xp of f, okay? xp of f, xp of f, and you smoothly move P. And so here you have point xq of f, okay? This defines a graph, okay? So therefore, in the whole thing is x of f. The whole thing is x of f. And once you set the point P, this is equal to xp of f, okay? Therefore, x of f is a function. M goes to R that define this graph. Do you understand? Therefore, x is C infinity of M to C infinity of M. F is some function that map manifold to R, but once you apply a vector field on F, itself some function over M. That's what means C infinity to C infinity. Do you understand? And which satisfy this condition. So at each point you have a linearity. At each point you have a Leibniz rule, because we already knew that the x can be written like this way. X at the local, if you use local coordinate, local coordinate, x can be written. Do I erase? It seems like I erase. Each vector field can be written at the local coordinate xi partial xi. Okay. The first, it's a first derivative, so it should satisfy Leibniz rule. Okay. Do you understand any question? Okay. And I just give you the so if two vector field there is of course, and also x plus f y is also vector field. Okay. Do you understand? Given the manifold f, m goes to R, so this vector field acts on f is just linearly acts on like this way. Okay? Like this way. I mean, it looks like a very trivial thing, but do you understand what I mean? Okay. And also, given the g in the function or smooth function on M, g times x is also vector field. Okay. G times x is also. Sometimes it's better not to mention. It's in mathematics language. Anyway. So, how about this one? X times y, is it vector field or not? So it's not your question. How about this one? So let's check. So x, y, let's check the Leibniz rule one by one. So y fn times g is the function of m, and it satisfies Leibniz rule. Right? Then so this itself is a function, okay? So we already know vector field is a map from function to function. Okay? So if vector field acts on function, itself is function. Okay? This one is function. So therefore, x can be acts on function. Then let's do step by step. And then apply Leibniz rule. X acts on this one, x, y, f, g plus some people already understand what I mean. And then x, f, okay, do you understand? So therefore, this is not equal to x, y, f, g plus f. Okay. You have extra piece. Do you understand? So therefore, they do not satisfy Leibniz rule. Okay? Do you understand? So therefore, x times y is not the vector field. Hopefully you understand that. Any question? Okay, so those are just property of the vector field. And then, so they just on some so they just form some vector space under the seeing infinity of n. But anyway, so let's not talk about it. I think you're getting bored. So we already know x times y is not the vector field. But how about this one? Let's not lose a hope. Let's not lose a hope. So what we have seen the extra piece here. So these are extra piece. Okay. These are extra piece. Okay. So we want to get rid of this extra piece. To get rid of the extra piece, what we can do is as follows. You swap the vector field, the order of the vector field, and take minus, negative. Then you can easily see that this one is equal to xy minus yx acts on f and the g plus f xy minus yx acts on g. Right? Even if you here, if you swap the order xy, y, it becomes yx. So they swap the order. Okay? They swap the order, but that is equal to this one. The same thing. So if you swap the order, that is equal to this one. If you subtract, they cancel each other. What's left is this one and minus swapped order, and this one minus swapped order. Okay? Exchange. Order is exchanged. So they satisfy vector field. Okay? So this is the element inside a vector field. Okay? Then people just write down this is x commutator of y. Okay? You understand? So this is called commutator. Or Lie bracket. Hey, if it's satisfied, so one is bilinear. What does it mean bilinear? This is bilinear. This Lie bracket is bilinear. Can you write down? What does bilinear mean? Can you write down? Does anybody? What's the meaning of bilinear? Can you come here and write down what does bilinear mean? I just write down in lecture note. I just write down bilinear. What does it mean? Just write down. Come here and write down.
I'm not sure.
It's just even if you make a mistake, it's okay. So, but you have to be careful. I mean, I think I prefer to use this notation. I think this is what he means. Thank you very much. And good try. And I think it's correct. I think I just try to interpret what he mean. So one has to be careful to state. So x, y, z are vector field. Okay, and alpha and beta is some r. I think that's what you mean. Hopefully, and this is correct. And the same thing for here: x, y, z. Okay, so this is what bilinear means. And 2, it's anti-symmetric. Means xy is equal to minus yx. And famously, it satisfies Jacobi identity. It is x, y, z. And plus everything cyclic. C. And the Jacobi identity. So this commutator or Lie bracket satisfied these 3 properties, and that's what you can check. Can you understand? So since we know that the f given a g, function g of x, so do you understand what's going to happen? Is it true that the Is it true? Is it true or not? It's true. So he said it's true. So show me. Show me. You hear it's true. So she said it's not true. How to show? How to show it's not true? I think you should write a bit bigger. Oh, maybe I. Okay, so then. Now you have enough space. You should write bigger. Okay, thank you very much. Wonderful, thank you very much. So this means y of f plus g times x, y, f. So forget about f, which means x times g, y is equal to x, g, y plus g times x, y. That's what she shows. Okay, so therefore if you look at upstairs, you have extra piece. Okay, so therefore that upstairs is not. Thank you very much. So therefore this up and better here has to be real number, not the function. That's what I want to say. Okay. Okay, we have still enough time, so let's go to flow. So flow. So the last time, not last time, just like a half an hour ago, we looked at the example. The vector field generated by x is equal to minus x1, x0, 0, okay? On S2 is the vector field is actually related to the rotation on the x2. Okay, that's what we have seen. So the vector field look like a. Anyway, so vector field is look like this way. Okay. What is the zero of this vector field? And south and north pole, so as you move to towards the north pole or south pole, the length of the vector becomes small because its absolute value is the coordinates. So at this point, x1 and x0 is 0. Okay, therefore it becomes 0. The length of the vector becomes small as you go to the north pole. And as I mentioned, so this should be related to the rotation of the x2, and then so this vector field will generate so-called flow that is the associated rotation of x2. That's so given a vector field, so one can create so-called flow or one parameter family of diffeomorphism. But that's too tongue twisting. So I'm not gonna use one parameter family of diffeomorphism. I just call it flow. So, my goodness, my shorts. So, as we mentioned, so you have, so given a vector field, one can just have an integral curve. So the vector field, you can have integral. You can integrate the curve and create the curve gamma of t. Integrate the vector field. So this curve gamma t should satisfy ddt of gamma t should satisfy. So let's consider the vector field x, which satisfy x of gamma of t. So this is an integral curve. Integral. So this gamma of t is called integral curve of the vector field x. So x is a vector field. And then locally, so if you take this point here, and then look at the open chart, you have the map to local coordinate which is x1 dot xn. So this equation can be written as follows: dxi dt is equal to so let's look at the x is equal to in the local coordinate xi partial xi when I is equal to 1 to n. So then this has to be capital X. So this is capital X, and I should write small x. X1 of t. So this is just a differential equation. Physicists are familiar with. So x1 is a map from. So there is a segment I to gamma t, from gamma t to the local coordinate x1 to the xn. So at the end of the day, so you have a map from I to some Rn, and you differentiate, you get some function. Okay, so that if you differentiate, this is equal to the xi coming from the vector field. So this is the differential equation, and one can solve this differential equation so that to get gamma of t, you need to solve this equation. So then there's always the solution for some interval. So that's a theorem 3.13. So the question is, isn't it always so? Given a point P, okay? Given a point P, if you solve this equation, okay, if you solve the equation, you have a curve, and can you move to at any point? The question is, this is not the case indeed. If you consider some open, some Riemann surface and Riemann surface, and just get rid of one point. So manifold does not have this point. Just get rid of one point, and consider smooth vector field. For instance, if the vector field goes to zero becomes zero around this point, one can smoothly define the vector field towards, for instance, one can consider a vector field something like look like this one. So we get rid of this point, but as you approach to this point, the vector field, the length of vector becomes very tiny. So as you approach to this point, the vector field becomes zero. Then it becomes a well-defined vector field, and you start with this point and solve this linear equation. Then you can get the curve, but as you move to the point here, this curve is no longer well defined. Okay. So the question is whether you can complete this flow or not. Depends on the topology of the manifold. Okay, the topology of the manifold. And then the question, if you can solve this linear equation and define if integral curve is defined for any t on M, it's called, the vector field is called, vector field is called complete. But as you can see, if you consider some manifold get rid of one point, and then create some nice vector field, then this gamma t cannot be defined for any t because it hits to the, eventually it goes to the the point you get rid of. So this is a theorem. The theorem is the smooth vector field is complete. So in this situation, one can define a map gamma. So integral curve always define so this is called flow. So let's look at this example. So you start with point P here, whatever point P here. So you can solve this linear equation, a differential equation, and that flow created this rotation, gamma of t, of P. And T is a rotational angle. Okay? Do you understand? T is really how many angle you just rotate corresponds to. So therefore, it's satisfied as the following: T plus S of P is gamma T, gamma S of P, and D gamma T of P, dt x gamma T of P. So this means as follows: if you just rotate a sphere along this x2 axis, so this is North Pole. So let's see. Let's look at the gray circle. And just rotate, how to say, again, it's hard to draw. So this rotation angle is can be t plus s, but t plus s means, so start with point P. T plus s means you just rotate only t, and only s, and again rotate t. It's a very trivial thing, but you just map point P by flow here, and then use the vector field at this point, okay? At this point, and use the flow to here is the same as you just rotate t plus s angle. It's just a one. That's why it's called one parameter family of diffeomorphism. But so this is called flow. This is called flow. So another way to see that if you consider R2 and consider vector field something like a partial x x1 plus partial x2 del x2 A, B. How does vector field look like? Or maybe no need A and B. How does vector field look like on R2? Can you draw? Can anybody draw the vector field in R2? How does it look like? How does this vector field look like? Can you draw? Let the other give a chance. Does anybody want to try? Does anybody want to try? I'm pretty sure he can answer. Just try. Even if it's okay, even if you make a mistake, just try. Just come here and try. So then you should try. R2. So it's a plane. So let's assume, so this is x2 and x1. So draw the vector field. Just whatever you think you can draw. Even if it's okay, you make a mistake. Okay, then one house should try. Should Good. Good. Do you understand what it means? So as I mentioned, the vector field form the. So these are the bases of a vector field. Pressure delta x1 is the direction of this vector. Delta x2 is this direction. And it's a linear combination, 1 plus 1, so it should be diagonal. And it's just constant, any point constant. At any point it's constant, so it should be, any point it should be the length, whatever, 1 square root 2 or whatever. Square root 2 on a diagonal line. And then what is the flow? What is the flow of this vector field?
That direction.
Huh?
Just flow to that direction.
It's called translation. So translation to the diagonal direction. The flow is this translation to the diagonal direction, to distance t. So gamma of t of p, you just start the point p and just go to the distance to t. Okay? That's a flow, okay, of the vector field. Okay, do you understand? Any questions so far? Any questions? Yeah, sorry, it's called one parameter, not family, one parameter group of differentials. Yeah, that's true. Differential is form of the group. Okay, so let's briefly mention orientation, and let's finish. So let's see. So you given the two bases. Okay, let's make it very concrete. X1 xn. So these are two local coordinates yn. Okay, two local coordinates phi of psi of the manifold. Whatever, phi and psi, x1 xn. Okay. So then we know that at the intersection between two charts, intersection of two charts, you have a coordinate transformation of the coordinate transformations. Let's see, for instance, yi is equal to phi x, phi y, I j xj. Okay, so that's the coordinate transformation. We already and we call it Jacobian. And if determinant of Jacobian is, yeah, of course, it's a coordinate transformation. It should be non-zero. So everywhere non-zero. Okay. If this it becomes zero, it's no longer how to say. These are no longer linearly independent. So there's something weird happens. So they're not good local coordinate. But so this is definitely non-zero. But the question is the sign. So if you take all the coordinate transformations is all positive, okay, then so then if this is the case, we call it x phi and psi have the same orientation. Same orientation, and otherwise it's not. And if you can find if all the coordinate atlas phi alpha on atlas on M have all the same orientation, then M, if one can find, atlas on M such that it has such that they have all the same orientation, the M is called orientable. Otherwise not. So all the Jacobian, so any intersection of the how to say chart, you can define a Jacobian, and the atlas given the local coordinate, if you can find all positive Jacobian, which means then M is called the orientable. Otherwise not. Yeah. So just give you one example. The famous example of the is a Magnus Strip. So if you start with the basis E1, E2 and move around, I always make a mistake. Let's see. So yeah, I think the easiest way is something like a E1 and E2, and just look at the normal direction on the surface. No, this direction, normal direction, E3. And as you move around the E1 and E2 and go back to here, as you move around, something like a E1, E2, and normal direction is something like this way, E3. So normal direction is just opposite, how to say, normal to the surface. Okay? And then go around to here. At the end of the day, what you will get is something like simply I should write down like this: E1 and E2, and the normal direction is the opposite. So the directions move towards the blackboard. Okay, so just schematically, I just draw like something like this one, E3. As you go around, the normal direction is opposite to the original one. The original one, it just, yeah, how to say? It just go towards you, but if you go around, it goes, how to say, toward the blackboard, the normal direction. Then you cannot see that, you cannot find a coordinate, local coordinate, that is the determinant, the intersection determinant is positive. You cannot. So that's a famous example of the non-ordinable manifold. Okay. Any question? Yeah.
Is it true that the Gauss-Bonnet theorem is only applicable to the orientable manifold, or it has a general formula for any manifold?
Gauss-Bonnet theorem can be applied for orientable manifold or not? Good question. Let me think. So, for instance, but what is the order to go climb bottle? That's the homework, right? Okay, then I will answer to your question after you do the homework next week. Okay. Because I mean, as you see, I mean, in the homework we have a climb bottle, computer record climb bottle. That is related to his question, so it's better not to answer him. So, yeah, so I will answer to your question. It's a good question. So I will avoid and try to think better. Yeah, yes.
I have a question. If the coordinate system go two circle, and this
So you mean circle around twice?
Yeah.
Then you go to the original one. Yeah.
Whether the mobile
Straight.
is orientable is based on how we move the coordinate system.
I mean, coordinate system. So if you go around, for instance, and we can take the following thing. So the locally, this is this patch, and then you can just consider the other patch like this way, right? So these two open patch will cover whole Magnus strip, and you just consider intersection between them, and then look at the determinant. Look at the determinant between them. So once you how to say? So these two open patch can cover whole Magnus strip. So it's enough to think only one circle. If you consider two circles, you have to consider two copies of these two open patch. Then, I mean, you just have two copies of the open patch and the two copies of the same Jacobian. But at the end of the day, you get some negative sign. Either side is, if you try to make it positive in one side, you get negative in the other side. That's what you end up with. Any other questions? Okay, so then, so as I mentioned, problem 4 is added on the homework one, so you should look at the update homework in e-learning, and you should try to at least solve homework problem 4. And it's due. You can either submit online by attaching PDF file, or you can bring the whatever your note and submit next lecture, whichever is okay. Yeah. Okay, so it's done.